Welcome. Today we're diving into the world of Hadoop and HDFS, two foundational technologies that have revolutionized how we handle massive amounts of data. Whether you're new to big data or looking to refresh your knowledge, this journey will clarify the core concepts and practical uses of Hadoop and its distributed file system. Let's start by understanding what Hadoop is, why it was created, and how it fits into the broader landscape of data management. Ready to explore the backbone of big data processing? Let's get started. Hadoop is an open-source framework designed to store and process large datasets across clusters of computers. It was developed to address the challenges of handling data that's too big for traditional databases. By distributing data and computation across many machines, Hadoop makes it possible to analyze vast amounts of information efficiently and reliably. This approach has transformed industries, enabling organizations to gain insights from data that was previously too large to manage. Before Hadoop, organizations struggled to store and process ever-growing data volumes. Traditional systems were expensive and couldn't scale easily. As data from social media, sensors, and transactions exploded, a new solution was needed. Hadoop emerged to fill this gap, offering a cost-effective and scalable way to manage big data. Its ability to run on commodity hardware made it accessible for businesses of all sizes, democratizing big data analytics. Hadoop is more than just a single tool, it's a collection of components that work together. The two main parts are the Hadoop Distributed File System, HDFS, for storage and MapReduce for processing data. Together they enable Hadoop to store massive files and run computations in parallel. Other components, like Yarn for resource management and various libraries, extend Hadoop's capabilities even further. Hadoop Distributed File System, or HDFS, is the storage layer of Hadoop. It's designed to store huge files by breaking them into blocks and distributing them across multiple machines. This approach ensures data is both scalable and fault-tolerant. If one machine fails, the data is still safe and accessible from other nodes. HDFS is the backbone that allows Hadoop to handle petabytes of information seamlessly. HDFS stores data by splitting files into large blocks, typically 128 MB or 256 MB in size. Each block is then replicated across several machines in the cluster, usually 3 copies by default. This replication ensures that even if a machine goes down, the data remains available. The system automatically manages these blocks and replicas, making storage reliable and highly available. HDFS uses a master-slave architecture. The name node acts as the master, managing the file system's metadata like file names, permissions, and block locations. Data nodes are the workers storing the actual data blocks. When you access a file, the name node tells you where the blocks are and the data nodes provide the data. This separation of duties keeps the system organized and efficient. One of HDFS's greatest strengths is its fault tolerance. By replicating data blocks across multiple machines, HDFS ensures that hardware failures don't result in data loss. If a data node fails, the system automatically recovers by using replicas stored on other nodes. This design makes HDFS a reliable choice for mission-critical data storage. Hadoop is built to scale. As your data grows, you can simply add more machines to the cluster. HDFS and MapReduce automatically take advantage of the new resources, distributing storage and computation across all available nodes. This horizontal scalability is a key reason why Hadoop is so popular for big data projects. MapReduce is Hadoop's processing engine. It breaks down large data processing tasks into smaller, manageable pieces. The map step processes and filters data while the reduce step aggregates results. This parallel processing model allows Hadoop to analyze huge datasets quickly and efficiently, making it ideal for everything from log analysis to machine learning. Yarn, which stands for Yet Another Resource Negotiator, is Hadoop's resource management layer. It allocates system resources like CPU and memory to different applications running on the cluster. Yarn makes it possible to run multiple data processing engines on Hadoop, improving flexibility and resource utilization. Beyond HDFS and MapReduce, Hadoop's ecosystem includes a variety of tools. Hive enables SQL-like queries, Pig simplifies scripting, and HBase provides NoSQL storage. Tools like scoop and Flume help move data in and out of Hadoop. This rich ecosystem makes Hadoop a versatile platform for all kinds of data processing needs. Hadoop's architecture is designed for big data. By distributing both storage and computation, it can process petabytes of information efficiently. Data is stored close to where it's processed, reducing network bottlenecks. This design is what makes Hadoop so effective for large-scale analytics and data mining. Hadoop offers several advantages. It's open source, scalable, cost-effective, and fault-tolerant. Its ability to run on commodity hardware lowers costs, while its distributed design ensures reliability. Hadoop's flexibility allows it to handle structured, semi-structured, and unstructured data, making it a go-to solution for diverse data challenges. Despite its strengths, Hadoop isn't perfect. It can be complex to set up and manage, and it's not ideal for real-time data processing. Hadoop's batch-oriented nature means there's often a delay between data arrival and analysis. Additionally, it requires significant hardware resources and expertise to operate efficiently. Unlike traditional file systems, HDFS is built for scale and fault tolerance. It's optimized for large files and sequential data access, rather than small files and random access. This makes HDFS ideal for big data workloads but less suitable for applications that require frequent updates to small files. When data enters Hadoop, it's first stored in HDFS. Processing jobs like MapReduce are then scheduled to run on the nodes where the data resides. This data locality principle minimizes network traffic and speeds up processing. The results can be stored back in HDFS or exported to other systems for further analysis. Security is crucial in big data environments. Hadoop and HDFS offer features like user authentication, access control lists, and encryption to protect sensitive data. Integrations with enterprise security systems further enhance protection, ensuring that only authorized users can access or modify data. Hadoop is used in a wide range of industries. From analyzing customer behavior in retail to processing sensor data in manufacturing, Hadoop's flexibility makes it invaluable. It's also used in healthcare for genomics research, in finance for fraud detection, and in media for content recommendation systems. In retail, Hadoop helps companies analyze massive amounts of sales and customer data. By processing this information, retailers can identify trends, optimize inventory, and personalize marketing. Hadoop's ability to handle both structured and unstructured data makes it ideal for these complex analytics tasks. Healthcare organizations use Hadoop to process and analyze large datasets, such as electronic health records and genomic data. This enables faster research, better patient outcomes, and more efficient operations. Hadoop's scalability and reliability are key for managing sensitive and critical healthcare information. In finance, Hadoop is used for risk analysis, fraud detection, and regulatory compliance. By processing vast amounts of transaction data, financial institutions can spot suspicious patterns and respond quickly. Hadoop's robust architecture ensures that sensitive financial data is stored securely and processed efficiently. Media companies use Hadoop to analyze user preferences and deliver personalized content. By processing clickstreams, viewing habits, and social media data, they can recommend shows, optimize advertising, and improve user engagement. Hadoop's ability to handle diverse data types is a major advantage in this fast-paced industry. Manufacturers use Hadoop to process sensor data from equipment, monitor production lines, and predict maintenance needs. This helps reduce downtime, improve efficiency, and lower costs. Hadoop's scalability makes it possible to analyze data from thousands of sensors in real time. Government agencies leverage Hadoop for everything from fraud detection to public safety analytics. By analyzing large datasets, they can identify patterns, improve services, and make data-driven decisions. Hadoop's security features are especially important for handling sensitive government information. A Hadoop cluster consists of many computers or nodes working together. Each node can be a commodity server, making it cost-effective to scale. The cluster is managed by the name node and resource manager, which coordinates storage and processing tasks across all nodes. Getting data into Hadoop is the first step in any big data project. Tools like scoop and flume are commonly used to import data from databases, logs, and other sources. Once ingested, the data is stored in HDFS, ready for processing and analysis. Once data is in HDFS, MapReduce jobs can be run to process and analyze it. The system automatically splits the job into tasks, assigns them to nodes, and collects the results. This parallel processing model is what allows Hadoop to handle such large datasets efficiently. After processing, results can be stored back in HDFS or exported to other systems. Tools like scoop can move data to relational databases, while others can send results to dashboards or reporting tools. This flexibility makes Hadoop a central hub for big data workflows. Monitoring is essential for keeping Hadoop clusters healthy. Tools like Ambari and Ganglia provide dashboards and alerts, helping administrators track performance, spot issues, and optimize resource usage. Effective monitoring ensures that big data projects run smoothly and efficiently. Many organizations now run Hadoop in the cloud, taking advantage of scalable storage and computing resources. Cloud providers offer managed Hadoop services, reducing the complexity of setup and maintenance. This integration makes it easier to scale and manage big data workloads. Hadoop is often used as the foundation for data lakes, central repositories that store raw data in its native format. Data lakes enable organizations to store all types of data, from structured to unstructured, and analyze it as needed. Hadoop's flexibility and scalability make it a natural fit for this role. Hadoop's processing power makes it ideal for machine learning tasks. Libraries like Mahout and Spark MLib allow data scientists to build and train models on large datasets. This capability opens up new possibilities for predictive analytics, recommendation systems, and more. While Hadoop is primarily batch-oriented, it can be integrated with real-time processing tools like Apache Storm and Spark Streaming. These tools complement Hadoop by enabling real-time analytics on streaming data, expanding the range of applications that can benefit from big data technologies. Data governance is essential for managing data quality, security, and compliance. Hadoop supports governance through tools like Apache Atlas, which tracks data lineage and enforces policies. This ensures that organizations can trust and control their big data assets. Visualizing big data is key to unlocking insights. Hadoop integrates with visualization tools like Tableau and Qlik, enabling users to create interactive dashboards and reports. These visualizations help make sense of complex data and drive better business decisions. Protecting personal and sensitive data is a top priority. Hadoop supports privacy through encryption, access controls, and auditing features. These tools help organizations comply with regulations and build trust with customers and stakeholders. Data backup is critical for disaster recovery. Hadoop's replication feature provides built-in backup, ensuring that data is safe even if hardware fails. Additional backup tools can further enhance protection, giving organizations peace of mind. Many industries have strict compliance requirements for data storage and processing. Hadoop supports compliance through auditing, access controls, and integration with security frameworks. This makes it suitable for use in regulated sectors like finance and healthcare. Hadoop has a vibrant open-source community. Developers and users contribute code, documentation, and support, ensuring that the platform continues to evolve. Commercial vendors also offer enterprise support, making it easier for organizations to adopt and maintain Hadoop. The future of Hadoop and HDFS looks promising. As data volumes continue to grow, these technologies will remain central to big data strategies. Innovations like cloud-native Hadoop, improved security, and integration with new analytics tools will keep Hadoop relevant for years to come. While Hadoop is powerful, there are alternatives like Apache Spark, Google BigQuery, and Amazon Redshift. Each has its strengths and is suited to different use cases. Organizations often choose the best tool for their specific needs, sometimes combining Hadoop with other platforms. Learning Hadoop and HDFS opens up many career opportunities. There are plenty of online courses, tutorials, and certifications available. Hands-on practice is key. Setting up a small cluster or using cloud-based labs can help you master these technologies and build valuable skills. Let's recap what we've covered. Hadoop and HDFS are essential for managing and analyzing big data. Their distributed, scalable, and fault-tolerant design makes them powerful tools for a wide range of industries. With a rich ecosystem and strong community support, Hadoop continues to be a leader in the big data space. Thanks for joining this exploration of Hadoop and HDFS. As data continues to grow in importance, understanding these technologies will be increasingly valuable. Whether you're a student, professional, or enthusiast, Hadoop offers a solid foundation for working with big data. Stay curious and keep learning.